Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Step on inside, and we are going to be doing an overview of things regarding exponential functions. Now to start off, there's a little practice on fraction bits to make sure you know how to work with them, how to multiply and divide them, even how to convert them to mixed numbers, which generally is not an ordeal that we work with. Once you hit pre-calc and onwards, improper fractions are all accepted answers. I mean, algebra 1 improper fractions are all accepted answers, but the thing is we're going to be graphing these. So when you get something like 16/5, you want to know exactly where that exists on a graph without use of a calculator, mind you. I'm going to avoid use of a calculator up until the very end where we use exponential growth and decay models in word problems. So I got to make sure to pop that up when we get to it. I have to remind myself to find that. I'll probably even pause the video to find it. So there is a front and back here. I'm going to have a PDF in the description down below and possibly timestamps as well when it comes to it. So I'm going to go ahead and get started right now. This is a practice quiz for my own group. The first set of problems we're going to convert just to mixed numbers straight up, and if we need to reduce the fraction, we will. You can either reduce before or after, one or the other, and I'll show you with the first problem. Here on out, you'll just see me reduce the fraction first and convert to mixed number afterward. So on number 1, we have 14/4. Converting to a mixed number means we need the whole value and then whatever remains with it. And that's literally what this is. 14/4 means 14 divided by 4. And if you use the long division approach, you would say 4 goes into 14 3 times, not wholly, because 4 times 3 is 12, and that difference there is 2. 3 is the quotient, 2 is the remainder, and there's a way to write that as a mixed number, which is 3 as the whole and 2/4, like this. Now, if you need to reduce this fraction, 2/4 can reduce to 1/2 in that you divide the top and bottom of this portion of the fraction by 2. Now, to put this into perspective regarding the fourths before I talk about the half in general, pretend like you had pizzas cut into 4 slices. That's what the out of the 4 is going to be, just to make sense of this. Cut into 4 slices like this. If you eat a whole pizza, you've eaten 4 slices. 2 whole pizzas is 8 slices, 3 whole pizzas is 12 slices. And if in this next pizza here, let's say you only eat 2 of the slices, in total you have eaten 14 slices of pizza that were cut into quarters out of their wholes. So 3 2/4 is akin to 14/4 in that same way. How does that really help you here? I mean, that's more of a logic conceit, but that's where the 3 wholes come from, right? And that's where the 14 comes from. That's where the 2 comes from as a remainder. Now, that's also 2/4 is also half a pizza, if that helps you. Now, that's one way to do it, converting and then reducing. I will generally, I don't know why I erased everything. I will generally reduce and then convert. So 14/4, the general question at play here is what can divide commonly on top and bottom? What is the greatest common factor of 14 and 4? In that case, that's 2 and 2. In dividing those, 14 divided by 2, 4 divided by 2 gives you 7/2. Still an improper fraction. In the same long division format, 2 goes into 7 3 times. 2 times 3 is 6, and 1 is that remainder. So 3 remainder 1 is indeed 3 and 1/2. I'm over speaking on this. This is something that I'm not downplaying the difficulty, what have you, but this is something you probably learned in elementary school. But speaking of it in all terms, just in case there's one version you do versus the other. Completely calculator free though. Make sure you reduce it when you get there. So you'll see me reduce number 2 before I convert to a mixed number. But there we go. So that's number 1, 3.5. Number 2, 100/48. Okay, there are different ways that people reduce fractions. I'm going to show you kind of 2 different forms if you didn't know that. Let's say you didn't know the greatest common factor of 148. Personally, I'm not positive of what it is. I can give a guess, and then if I'm not sure, you keep reducing. And that's something you can do. For example, you can say, I know these are even numbers, so I can divide them both by 2. Maybe it's not the greatest common factor, but I can do it. I get 50/24. And you're like, okay, I know these can divide by 2, and then I get 25/12. And then you actually can't reduce any further. And that was I was guessing that 4 was among them. I didn't know if it was the largest, but there it is. 25/12. Now, before I convert to a mixed number, let me show you the alternative. This one's probably a little overzealous, but let's say that the numbers were, I mean, these numbers are kind of big, but let's say that the numbers were like astronomically bigger. Another good version is using what's called prime factorization, where you take the 100 and you start splitting it up into factors like 10 and 10, and then 10 splits up into, 2 and 5. And you break up 100 into prime factors so that 100 is 2 times 2 times 5 times 5. All 4 of those multiplied together equal it. And I put them in order so they're easier to know which numbers you put and all that. 48 can break up into, let's say, 6 and 8. And 6 can break up into 2 and 3. 8 breaks up into 4 and 2. And 4 breaks up to 2 and 2. So 48 is 2 times 2 times 2 times 2 times 3. These prime factors here are a breakup of that. 2 times 2 times 2 times 2 times 3. That's a lot of work just to do that for this problem because you only have to divide by 2's. But what you would do is you would say, what are common factors on top and bottom that you could then divide and cancel? 2 over 2 right here, 2 over 2 right here. Nothing else can divide. All that's left on top is 5 times 5. And all that's left on bottom is 2 times 2, which is 4, times 3, which is 12. And you get 25 12s. So if numbers are really big or really extreme or you're really uncertain, that greatest common factor is massive. This is kind of a cool go. This is also kind of a cool go. Just divide when you know what you can do with it. Not every set of numbers is always even like that to do it. But if you know your divisibility by 3 rules and 9 rules and stuff like that, 5 obviously, those are nice as well. Anyway, 25 over 12 is the improper fraction here. So what is that mixed? It's a reduced improper fraction. So what is the mixed number equivalent? 12 goes into 25 twice to get up to 24. And then there's one more remaining there. That's 1 out of that 12. Remember, it's the out of 12 there. Denominator doesn't change unless you're reducing the fraction, which we already did. 48 would have gotten to 100 2 times with 4 as remainder. 96. Yeah, 4 48s, and that reduces to 1/12. So there's number 1, 3.5. Number 2, 2 1/12. I'll go faster on the converting to mixed numbers bits because we're going to be doing them on each problem, but there is the idea. All right, find each product or quotient after reducing any improper fractions, convert them to mixed numbers. You even see how I'm stating reduce first because we're not going to be converting to mixed numbers all the time. I mean, we are in these problems here, but generally improper fractions are good. So don't think about mixed numbers first before you think about reducing first, please. That's a general idea I'm going to ask. Now, this one is a mixed number to start. We have 5.5 times 3/4. And what you don't do is you don't just multiply the 1/2 times 3/4. You actually have to multiply 5.5 with 3/4. Technically, 5.5 would be 5 plus 1/2. And multiplying by 3/4, which means you'd have to distribute that. And I'm not a fan of that form of working that out. I'd rather instead convert this to an improper fraction because multiplication of fractions just means multiply across the top, multiply across the bottom. Now I'll show you some little tips and tricks that I do along the way if this thing can reduce in this other fashion. I don't know if this problem does, but some other problems might. All right, if you consider 5.5 as a mixed number, converting to an improper fraction in pizza form would be, if these pizzas were cut in halves, I'm going to eat 5 whole pizzas. 5 whole pizzas is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 slices. And then half of another pizza here. So that is 10 plus 1. So what you're doing math-wise is we're doing 2 times 5, 2 slices per pizza times 5 pizzas, plus the 1 remainder there. So multiply and then add. And that becomes 11. So 11 slices of pizza out of 2. That's the math in that. If I ever have to do it again, that's what I'm going to do for you. I might not have to. Times 3/4. Right there. And we multiply. Now, one little thing that I look for is if you understand that this does become 11 times 3 over 2 times 4, that means that 11 was always dividing by 4 this entire time, and 3 was always dividing by 2 and 4, right? They're dividing by both. But the reason I bring that up is because instead of needing to join these, I want you to note that through multiplication, 11 is not just dividing by 2, it's also dividing by 4. So if you can reduce something beforehand, I recommend you do it. It saves you from getting larger numbers and figuring out if you have to reduce later. Now, 11 over 4 doesn't reduce, much like 11 halves doesn't, and 3/4 and 3 halves do not reduce. So there's nothing I can do there. So I'm just going to multiply straight up And if that couldn't reduce before, then of course this can't reduce now. So this would be a good answer, but it's an improper fraction. So we're going to convert to a mixed number. So 8 goes into 33 4 times because you get to 32. And 1 is a remainder because we add up to 33, and that's 1/8. So 4 and 1/8 is the answer there. All right, number 4. Negative 2/7 divided by 8/21. No mixed numbers to convert here, so it's just division at this point. Now, there is a negative. So what I'm going to state straight up is, hey guys, our answer is going to be negative. I'm going to ignore. Some people think too much about the negative. They make it harder for themselves. Really cover it up and say, a negative divided by a positive is negative. Just look less on that. Really focus on 2/7 over 8/21, right? Take away things that are distractions to you. Distraction with fractions. So the division is also kind of a concern for me that I want to work on. And dividing a fraction means multiplying by the divisor's reciprocal. So this thing right here, 8/21, I'm going to flip as I change the division to multiplication. Negative 2/7 divided by 8/21 is also negative 2/7 times 21/8. Now, again, we know that the negative is going to be there in the long run. If you're asking, do I put the negative on top and bottom? You can ignore it. But to answer that question, you can put it in either. The idea is it's not the 2 or the 7 that's negative. It's 2/7 that's negative. If you'd like to, you can assign it to the top and just negative 2 times, all that. Or the bottom, but not both. Negative over negative is a positive. It's not both. That's why I'm saying kind of ignore it as much as you can. Let me kind of not get rid of it. Let me put it here. So, all right. So here's the thing. You can do 2 times 21, 7 times 8 and get those, but you will have to reduce that fraction. I recommend you reduce earlier on so you can have smaller numbers to reduce with, and then you have smaller numbers to multiply. Not that 2 times 21, 7 times 8 are difficult, but if they were, right? If they were, that's something to deal with. And so that's a good strategy to employ. So how's that strategy going to work out? 2 7s can't reduce, 21 8s can't reduce, but 2 8s can reduce. That would give us 1/4. 21 7s can reduce. That gives us 3/1. 1 times 3 is 3. 1 times 4 is 4. The answer is negative. So we will end up with negative 3/4. See, if we multiplied before, we would get negative 42/56. And then you got to find out that 14 is the greatest common factor of both of those, or divide by 2 and 7 and, work that out. But if you reduce earlier on, I do think it helps you in the long run. Obviously, reducing smaller fractions is easier than larger fractions with that. All right, numbers 5, 6, and 7. Simplify each expression by making use of the exponential properties and their rules. Any fractional values must remain as fractions and be reduced. What I mean by that is you're not using a calculator and you're not writing a decimal. We're going to keep them as fractions. We're going to convert to mixed numbers if they are improper, and of course reducing. So number 5 says 10 to the 0 powered. Straight up, that answer is 1. The property stated is that any non-zero number to the 0 power is 1. So there, that's your property. Any non-zero number to the 0 power is 1. 0 to the 0 power is an indeterminate. We're not going to run into those. I'm just stating the property for future reference and correct math with it. That's not the answer. That's just a property. Okay, so that's number 5. 10 to the 0 is 1. Now, be careful when it comes to order of operations. If there was some sort of 6 right here, 6 times 10 to the 0 power, you would do 10 to the 0 power first to get 1, and then you'd multiply by 6, right? So order of operations apply to that. Just, be very cautious on that level. All right, number 6. The property and use that we can apply here is that when you have a product or fraction that is raised to an exponent, you can raise each portion of that factor or, that fraction, numerator, denominator, to that exponent. And we'll do it before we multiply the 6. 6 doesn't multiply with 1/3 before 1/3 gets squared. So we are going to begin by squaring 1/3 by squaring the 1 and squaring the 3. That's kind of, it's almost a distribution, if you will. That's not the official term, but that's equivalent to what you're doing. So 6 times 1 squared is 1 and 3 squared is 9. We have 6 times 1/9. Now 6 does not multiply with both the 1 and the 9. 6 is a numerator value. 6 is dividing by 1. 6 only multiplies with 1 as 1 multiplies with 9. And I mean, it's in my veins to want to reduce now, despite the fact it's going to leave you 6/9 still. But 6 does divide by 9 right now, and you can reduce by dividing both of those by 3. And you get 2 over 3. 2 times 1 is 2, and 1 times 3 is 3. You get 2/3. That is your final answer. Number 7, we have 4 times 2 to the negative third power. Now, we do the exponent first, and the rule within this is that a negative exponent in a numerator becomes a positive exponent in a denominator. The one thing you need to be careful of is that it is not going to become 1 over 4 times 2 cubed. The 4 has nothing to do with the negative 3 exponent. I'm going to repeat that. The 4 has nothing to do with the negative 3 exponent. 4 is being raised to the first power all on its own, right? It's like its own thing. 4, if you want me to separate this thing, perception is reality for people. If I turn this into 4 times 2 to the negative third, people see that a lot more as, oh yeah, it's just that thing, right? So the 2 to the negative third would become 1 over 2 to the third. So that equals 4 times 1 over 2 cubed. Now, I generally don't write it this way as a multiplication here, so it's over 1, all that. What I do is, even though there's not a fraction, I would kind of take it and like bring it down. So it'd become 4 over 2/3. It's neither here nor there, but the idea is that ultimately this is what it turns into, right? 4 times 1 is 4, 1 times 2/3 is 2/3. I keep saying 2/3. I'm sorry, 2 cubed. If I said 2/3 over and over, my bad. I was thinking negative third power. 2 to the third. Now we have to evaluate 2 to the third, right? 2 times 2 times 2, that's 8. So this equals 4/8, and 4/8 reduces to 1 over 2. Now, still another order of operations thing. You can't take 4 over 2 and reduce it to 2 over 1 because it's not going to be the same answer. 1 cubed is 1, and 2 divided by 1 is not 1 over 2. It's 2 over 1. It's a different answer. You have to use the exponent first before you do division. So order of operations apply, of course, and there's your final answer. No decimals, no calculator. We're staying without a calculator throughout. All right, number 8. Fill out the tables for the following functions, continue reducing fractions, and converting to mixed numbers. So continue that whole ordeal. The idea behind this is if you ever want to graph using a table, you may. And when I say using a table, I mean plugging the x values in to get the y values out. That is something you can do. On the back side of this, I will not be using that format, but it's something that you're able to do. But right here, part of the property bits, let's check and see what we got. I will start actually with the bottom. Let's go from 0 to positive. I argue that they're easier. And what we're going to do is substitute these values in for x, get the y value, write the ordered pair. And that's all good. Because the idea is we could graph these, right? So we have 10 times 2 to the 0 power. This is perfectly in line with what I was bringing up before. 2 to the 0 power is 1, and we do 10 times then 1, which is 10. So the y value for that is 10, and we get 0, 10. Now, if you've been following me with graph things, in the last video I had regarding exponential functions was graphs, you probably learned a little bit on this and what you can do to get these answers a lot easier. For one, in y equals ab to the x form, a is your y-intercept, so it's 10 automatically. For my own kiddos, I need them to show their work on the quiz and to show me what I'm testing them on their properties. I'm testing them on their knowledge of exponential properties, being able to reduce and things like that. When they want a graph, they can do whatever they want. In the table, they're kind of confined into doing this. So just, it's good to know the properties because we don't always have numbers with them. We have variables, etc., and we want to know what to do with them. Especially when, look, maybe you're not good at that other exponential stuff. All right, 2 to the first is 2, and 10 times 2 is 20. So the y value being 20 means we get 1, 20. This is going to be 10 times 2 squared. And 2 squared is 4. 10 times 4 is 40. I'll go relatively fast with these. There's not much to be had here. Now, some people might ask, where are these numbers coming from? These are the x values. There's the 2. X is 2. Y is 40. 2, 40. 2 cubed, we saw before, was 8. If I say 2/3, I apologize. And 10 times 8 is 80. Easy numbers. Easy peasy. Super easy. Barely an inconvenience. It's not my phrase, by the way. It's Ryan George's phrase from Screen Rant? Pitch meetings? All right, let's raise 2 to the negative first power. Now, that same kind of thing, actually, I don't know which way. I stated before, I think I just bring the fraction down. I don't know if I do that now that I think about it. Do I write that personally as 10 over 2? Or do I write that personally as 10 times 1/2? You know, I actually might do this. I might actually write it as 10 times 1/2. And I will. But 10 does divide by 2. Right? 10 over 1 times 1 over 2. 10 does divide by 2 here. And 10 over 2 is 5. And 5 times 1 is 5. 10 times 1/2 is half of 10. That's 5. So negative 1 comma 5. 10 times 2 to the negative second power is 10 times 1 over 2 squared. Right? By the way, why was this 1/2? That's 2 to the first. Right? 2 to the negative first power is just 1 over 2 to the positive first. And 1 over 2 squared is 4. So this is 10 times 1/4. Now 10 is dividing by 4. And so when that is, both of these can divide by 2, and you get 5 over 2. 5 times 1 is 5. So you're left with 5 halves. Now I did ask you to write these as mixed numbers. So, or the instruction is to write them as mixed numbers. 2 goes into 5 twice. That's left with 4 plus 1 equals 5. So 1/2, 2.5 is your remainder there. So negative 2 comma 2 and 1/2. And lastly, the negative 3 here, 10 to the negative third power. And you might notice here, you know, this, let's see if I can find them. This number 2 is that number 2. This number 4 is that number 4. And this number 8 will then be this number 1/8 right there. So this is going to be 10 times 1/8. No tricks up my sleeve for that. Right, those numbers that come into play are what's being raised to the first power, second power, and third power there. Now 10 over 8, remember, it's dividing. No matter how I write this thing, it's dividing because 10 is divided by 1. 10 over 8, divide those both by 2, you get 5 over 4, and that's what this fraction is. 4 goes into 5 just once, with the remainder of 1, that's 1 1/4, so that's negative 3 comma 1 1/4. Now, the improper fractions are still really relevant when it comes to us graphing. And we're done with the problem, but we're about to graph exponential functions as well of this variety. And what I'm going to do, again, I'm going to avoid use of table work. It kind of takes a moment to do. And what you probably know from y equals ab to the x power with me is that the I mentioned this before, the a value is the y-intercept. When x equals 0, we get 10. And the 2 represents the growth factor, which states what you'll multiply from one y value to the next, as in times 2. 10 times 2 is 20. 20 times 2 is 40. 40 times 2 is 80. Not allowed to do this in the table stuff when I ask you to exercise exponential properties, but we will later. So if we multiply by 2 when we increase x by 1, then decreasing x by 1 means we divide by 2. And 10 divided by 2 is 5. And 5 divided by 2 is 2.5. I know most people probably know that, but we first initiate it as maybe 5 over 2. And that can be helpful for you. I know that you can write 2.5 here, but what happens when you do 2.5 divided by 2? And 1 1/4 divided by 2? And, you know, that next number divided by 2? What happens when you have those? Well, what I recommend is we know that dividing is multiplying by the reciprocal. So if you divide by 2, and we're going to do this on the next page likely, dividing by 2 is multiplying by 1/2. And I don't want to do 2.5 times 1/2. I want to do 5 halves times 1/2. 5 times 1 is 5. 2 times 2 is 4. You get 5 over 4. You can convert it to its mixed number state. So even if I'm asking my students to show work with these problems right here, you can confirm that your work is good. If another student asks me, are these answers right? I'm going straight into the whole, is your y-intercept good? And are you doubling? And are you halving? I'm straight up doing that personally. So there's that. All right. That was number 8, and let's move to the backside where we graph. We describe whether it's positive or negative growth or decay. We get our domain and range with these and the y-intercept and all that with the graphs. And I might zoom out on this a little bit, all depending on what I need to fit. And then we have word problems down here. All right, graph each exponential function, including its asymptote. Plot at least 2 points on each side of the graph, or as many as you can fit on the tall side. Identify all requested features below. as well. We start with y equals 3 times 2 to the x power. So when it comes to, let's start with the features. When it comes to the features here, the y-intercept is your a value right here. So a equals 3. This is y equals ab to the x, right? Y equals ab to the x. The a is 3. That's your y-intercept. And a y-intercept is where we cross the y-axis, or the value of y when x equals 0. This is 0, 3, and that's a plot that we're going to point. That's our reference point. The domain straight up, non-contextually, without word problems, we'll get into word problems later, but your domain will be all real numbers for all exponential functions, which basically states that there is no restriction on x that we could ever substitute into here. I can substitute anything from negative to positive infinity, including 0, and you'll always get a value out for y. Word problems can be exceptions, either because maybe you can't have, it's with respect to time, and maybe we start at time 0 in the context of the situation. Maybe we can't have, what's the phrasing? Maybe we can't have decimal values. Maybe you can only have like at time 1 and time 2 for specific things. Things like that. So you might be restricted on your domain there. Here, not a problem. Now your range, the idea regarding the asymptote that I want to state here is there is no translation on these graphs. We don't have like a -7 plus 5 going right here. There's no horizontal vertical translation. Your asymptote is on the x-axis. The asymptote meaning a dotted line that we're going to be drawing on graphs here that represent this barrier that says our graph does not touch or cross. Because when we raise 2 to positive exponential values, this thing is going to skyrocket and take off. Has to do with exponential growth. When we raise them to negative exponential values, very large ones, it's going to be dividing by 2 to that positive power. And it's going to make our numbers really small. Really small as in really close to 0, but not 0. No matter what I substitute for x, these values will always be positive. And I can touch every positive number under the sun. Every single one. 2.4, I can get it. There's an x value for it. 0.000912, there is an x value for it. It exists. 1 billion, there's an x value for it. Y is greater than 0. This is our range. And if you want to graph it beforehand to construct domain and range, that's totally fine. That can help you with it. I just said I'd identify these things first. Because a is a positive number, this is a positive exponential function, point blank. Because b is greater than 1, this is exponential growth. And again, these might be things you need to see after you graph it, and I'm understanding of that if you need to. Let's go ahead and draw the graph, and I'm going to zoom out on this bad boy right there. All right, let's zoom out. So y equals 3 times 2 to the x power. First thing I mentioned was that horizontal asymptote, something which maybe we can see after we graph as well to make sense of why it's drawn. But it's a dotted line on the x-axis, and unless there's a vertical shift, it will stay on the x-axis. Okay, I'm going to start at the point 0, 3. That's how the 3 exists in this problem. The 2 does represent growth, and by growth I mean that as you increase x, then the y, it's not that the y goes up, it's that you are, well, it goes further, it separates itself from the asymptote. This 2 states how many times you've multiplied by 2 over and over from 3. As I increase x by 1, I'm going to double my 3. I get 6. As I increase my x by 1, I'm going to double. Why am I saying double? Because 2. I'm going to double my 6. I'll get 12. As I increase x by 1, I'm going to double my 12 and get 24. Not really on the graph, but if you want a general idea, it's about up there. And as I decrease x by 1, I'll be dividing by 2. I just mentioned this on the other side of this page when it comes to dividing by 2, also meaning multiply by 1/2. And I want you to get at least 2 points on this thing. So I'm going a little smaller, zoomed in right now. 3 divided by 2, half that distance is indeed 1/2, right? 3 divided by 2 is 1/2, and we get that. If you're not sure about that, again, no calculator usage, do 3 times 1/2. That's what we're doing there. Now, 1/2 divided by 2, that's a little tricky to kind of say out loud. So instead of doing 1/2 divided by 2, take its improper fraction equivalent, 3/2, and divide that by 2, or multiply it by 1/2, and you get 3/4. You can approximate that one. It's more than a half. It's halfway between a half and 1. So 3/4 is right there. I'll continue the idea of this just to plot more points for you, even though this would all be that's required on a quiz, something like that. A half of 3/4 divided by 2, half of 3/4 is 3/8. It's a little less than a half because 4/8 is a half. And then 3/16. And you can see that shrinkage, but it never hits 0. It never hits 0 when it comes to asymptote stuff. Asymptote stuff. So I'm going to start with that part. I'll kind of take off on the other side there. It gets closer and closer. You know, I'm that half arrow guy up there. And then up here, I can try my best to kind of like get that there. But when I say graph as many points as you can on the tall side, you already got 2 points on this side, and that fits on the tall side up there. At that point, if you want to draw an arrow there, that's fine. I'm just getting a little more precise for you because, you know, I'd rather do more for you than less. Tailored toward the smallest, the least common denominator. All right, number 10. Let's get the information. Oh, hold on. Let's confirm number 9's information. 0, 3 is the y-intercept. That's kind of what I graphed first. Domain's all real numbers. The arrows kind of indicate. This isn't going straight up, by the way. This is going very steeply, but it is still going right? If I increase x by 1, I'm going to double 24 and get 48. Double 48 and get 96. Double 96 and get 192. And it keeps going as I increase x by 1. It goes really sharply, but it doesn't go vertical. So the domain, it goes forever right as it goes up. And it goes forever left. It gets closer and closer to the asymptote. It gets like 0, but it's not 0. And that's where the range jumps into play. Y is greater than 0 states that every y value is hit in the world that's positive. It never hits 0. It never hits negative values. And that would be your range. All right, number 10. How far have we gone? 30 minutes? 31 minutes? All right, number 10. Y equals -4 times 1/2 to the x power. We'll start with the y-intercept being the a value. That's at 0, -4. Domain, once again, will represent all real numbers. Not trying to trick you on that one. Not trying to trick you on this one either. We have a negative a value. We're going to have negative y values as well, or underneath the asymptote, I should state. Now, this graph kind of reveals that to you. To make this graph tall, in sacrificing making the graph tall, I gave you kind of the window of where you would be graphing. So for this one right here, that range is going to be y is less than 0. All your values are negative. If we now have a horizontal asymptote on the x-axis, or if we still have a horizontal asymptote on the x-axis, our points are now going to be below this. The idea is we're going to start at -4, and we're going to be multiplying by 1/2 or dividing by 1/2 over and over. Taking a negative and multiplying or dividing by a positive will leave you with negative numbers. I'm going to stay negative no matter what I do. They're never going to turn positive, and they're never going to be 0. Keep taking half of something over and over. Gets close, but doesn't do it. Now, so it is a negative graph. It's a negative function. And it's also decay. B, what I stated before was if B is more than 1, it's exponential growth. Now, not that this is the graph, but this would be considered, by the way, guys, negative growth. This is distancing itself from the asymptote as you increase x. This would be doubling -4 and doubling -8 and doubling. That is considered negative growth. Not what this is. This is negative decay. Our graph is going to go this way. But decay is when b is between 0 and 1. Basically when you see a regular, proper fraction on this thing. Decimals can apply. In fact, we will have decimals right here. They're equivalent to fractions, but this is where we accept decimals because of the nature of the problems. Right here, we're going calculator free, working this stuff out, and we're going to go ahead and graph it. So I'm going to start with -4 as my y-intercept, and we're going to be multiplying by 1/2, which means dividing by 2, whichever way you want to put it. I like when I'm using integer to integer, I like to say divide by 2. -4 divided by 2 is -2 as I increase x by 1. -2 divided by 2 is -1. And -1 divided by 2 is, well, yes, -1/2. Let me zoom in now. -1/2. -1/2 divided by 2 is -1/2 times 1/2, which is -1/4. And going, obviously I'm going more than would be asked of you. You'd only need those two. These are relatively easier questions. I do wish I gave you a more difficult one. I'm going to say it right now. This was set for integrated math 1 to begin with. I probably should have changed the problems to get like 2/3 and things like that. So don't be surprised if you see something like that ever surface. That's, that's where a problem can get a little trickier. That was 1/4. You can have, negative, so negative 1/8, etc. It keeps getting closer. Multiplying by 1/2 as we increase x by 1. Dividing by 1/2 as we decrease x by 1. So when you do -4 divided by 1/2, hey, there's an easier way to say that. That's -4 times 2, because we multiply by the reciprocal of the divisor. So we flip it, -4 times 2, that's -8. So we're doubling going this way. -8 doubled is -16, and we fit what we could. I'm not going to try and insert -32 into that. All right, so let's go ahead and construct that guy. It's going to be kind of like this. Again, all real number domain, as we stated before. The range is y is less than 0, not equal to 0. And those are our two graphs. No table. You can use a table. I'm not stopping you. Not much room, though. All right, final two questions, growth and decay formulas. So here's kind of a weird looking formula, but it's provided for you. The idea of this is in these word problems with context, you'll see them when we read them, but you're going to have some sort of percentage increase or decrease of something. We start at some number. We're going to increase or decrease some percent of that thing, like when a population grows by a certain percent, whatever. I'm sure that's going to happen. Oh, these are both dollar amount problems. But you can increase something by a percent, say like a bank account thing, interest. That's what the first one is. But we're not just going to do it once necessarily. We can do it multiple times. We can increase that by that percentage over and over again, 100 times, 1,000 times, 1,000,000 times, or in one case, 3 times, and something like that. So, but when that comes into play, that's where exponents work, right? If you increase something exponentially, if you increase something percentage-wise and do the same thing over and over, you're multiplying by the same number over and over. That's what exponents are. And that's where this growth and decay model comes into play. So when you're looking at this thing here, and I'm giving you all the information, A is your original number, your initial investment, the initial car value, the initial population, whatever it is, A is that y-intercept, because at time 0, right, that's at time 0, that's when this thing starts. R represents the rate of this thing. It's a percent in decimal form. So I know I don't have a video on this yet, so this is kind of your first that you're seeing it. And T is the time period, whatever's represented there, and make sure that you enact it based on year 0 being your initial value. And you maintain the units there. All right, let's look at a problem here. We're going to write an exponential function to model a situation. That means that T, the variable T, should exist in that before we answer the question about 3 years and in 2021. Find each amount at the end of the specified time, round populations to integers, and dollar amounts to 2 decimal places, because we can get cents out of that. Round all other values as requested. If I asked you to round to the nearest tenth for something, do so. Things like that. All right, number 11. Suppose you deposit $2,000 in a savings account that pays 4% interest compounded annually. How much will be in the account? How much will be in the account after 3 years? So when it comes to the model, the 3 years part is ignored. The model is just the suppose you do this. That's supposed to be crossed out. The model is just for this part right here. For any amount of years, T years, for T years. Now the equation says y equals A times 1 plus or minus r to the t power. Here's how we're going to break this down. Your A value is your initial investment, $2,000. Your R is in reference to this percentage right here. Now we need the decimal equivalent of 4%, which is 0.04. That's 4 divided by 100. 4% is 4 out of 100, which is 0.04. You can take a decimal and shift it 2 places over, and that's what you would be getting. Right now, T is T, for the sake of this equation here. The last part that you need about this, you notice this plus or minus. We're not using both. We're only using one of them. Something is going to be, you deposit something, and it's going to be, when you say pays, you might be thinking that you're paying something. No, it's paying you. The savings account pays you interest. It pays you interest. This is growing. So what you're going to do is, R is 0.04. We're going to substitute these things into here, and we get 2,000 for A. This is 1 plus 0.04 to the t power. Now, why is the 1 here? Because if you just multiplied by 0.04, you'd be taking 4% of 2,000 and then 4% of that number. We want to get a 4% increase. And the 1 is there because 2,000 times 1 is 2,000. 1 represents a whole. 1 represents 100%. When you are getting 4% interest, they're giving you 104% of what you previously had. 100% of what you had plus an additional 4. And that's what these are in decimal form. And the decimal is the true calculation of what we use. Percentages are not the true calculation. That's a number that's 100 times larger than your decimal. Let's simplify this to 1.04 to the t power, and I'm going to leave it like that. That is our model. That's our model for this function. You could even graph this. You could get a graphing calculator and graph it, and you can see for any time t how much money you'd have in this account. We want to see how much is in the account after 3 years. So what I'm going to do for the 3 years is I'm going to substitute 3 for t over here for amount. So that's going to say y equals 2,000 times 1.04 to the third power. I forgot to get the calculator out. So I don't know if there's something I can state out loud while I'm getting this thing open for you. Give me one moment. It's that right here. So I'm opening my calculator thing, and what I'm going to do is I'm going to straight substitute. I'm going to type this out directly. There's nothing else I have to do other than that. Oh, hold on a second. I was using a graphing calculator. Let me pause this in a second. But I was using a scientific calculator emulator, and my trial expired for it. So I'm going to go back to my graphing calculator one. Give me one moment. Okay, I think I'm back. I'm back. Okay. So I have this cleared. All right, perfect. Okay. So I have this cleared here. So here's what I'm going to do. So I'm going to type this 2,000 times 1.04 cubed into this calculator here. So I'm going to straight up 2,000 parentheses 1.04 raised to, and you can use this kind of thing or an x to the y power or something like that, raised to the third power. This is going to know the order of operations. It's going to do 1.04 cubed, and then it's going to multiply by 2,000, or whatever. It's going to do that. So basically what it's doing, what our calculation is, not thinking of the calculator, 1.04 cubes means 1.04 times 1.04 times 1.04. What you're doing is you're taking your $2,000 initial investment at year 0. After 1 year, it's going to multiply by 1.04. You get some number, more than 2,000. After year 2, you take that number and multiply by 1.04. And after the next year, multiply 1.04 again. And this is doing it in kind of a simplified manner. And what you're doing is each number becomes larger, and when you multiply by a larger number, you get a larger difference than the previous amount. That's why exponential functions do what they do. Like double 4, you get 8. That difference is 4. Double 8, you get 16. That difference is 8. Anyway, so the idea is that's what we're doing with the calculation, and we get this computation here. We get 2249.728. Let me write that down to start with. 2249.728. By the way, I wish my savings account did this percentage. That would be incredible. Here we go. So that is this right here. Now that's not an answer because this is contextual. This is dollars. Dollars should have 2 decimal places, and it should have the dollar sign. So I'm going to put a dollar sign there. $2,249 and let's round to 2 decimal places, 73 cents. Now, there may be some other videos I have in my thing where you see me do something like truncate this thing and say, you don't have that 73rd cent yet. It hasn't been earned. We can't round and just assume. And that's something that I've done in the past. That's something that I would continue to do at some points in the future. Not right now. This is just more so, are you applying the model context? Are you understanding the situation? Some of the other math teachers aren't doing it as well. So if a student from another class is watching, I want to make sure that you're getting a good idea of what you're doing there. All right, last problem here, number 12. A brand new 2016 Toyota Tacoma Sport had, because it's not 2016 anymore, had an MSRP, manufacturer suggested retail price, of $38,180. Its value depreciates at an average rate of 9.8% annually. Annually, by the way, means every year. And if you hear like biannually and things like that, like those would mean different things. I think biannually is twice a year, not once every 2 years. What is the value of this vehicle in 2021? When I made this worksheet, it's 2021. Now it's 2022. I should update this. hint how many years have passed since 2016. And this is important because when it says the 2016 Toyota Tacoma, it had this at year 0. It was brand new then. This is its y-intercept. This is the A value. This is the initial amount. And so when you do 2021, we're not at that part yet, but when we do 2021, you got to think of how many years came after 2016, because I'm not going to plug 2021 in for T. The Toyota Tacoma Sport did not come out in 0 AD. Christ was born and the Toyota Tacoma Sport launched, right? It was in 2016, and then this was years later. But we're starting with the model, not even T. I just want to make sure you understand this is still an initial y-intercept, initial value. Now 9.8 represents the R value, but the R value in itself, if you shift 2 decimal places, is 0.098, not 0.98. That would be 98%. So as far as the model, oh, and last thing, this depreciates. You can appreciate or depreciate. Appreciation is growth, depreciation is decay. So instead of 1 plus r to the t power, it's 1 minus r to the t power. So we are going to do y equals a, 38180 times 1 minus r to the t power. A couple mistakes people make, or a couple things I want to point to my students out about. Number one, you need the 1, right? We're not just going to have 0.098. That's taking 9.8% of your number. That Toyota Tacoma is losing value really fast. You're basically, this would become a $4,000 car or whatever after a year. No, that's not what's happening. We are decaying. We are taking away from 100%. It's like having a sale. 20% off does not mean it's 20% of its value. It means take 20% off of the value. It's 80% of the value. So we're subtracting from 100%. Number two, also just as bad. I appreciate the negative thing, but it's not negative this number to the t power as well. It's 1 minus it. Second and third thing, don't forget the t. Don't plug in your t value yet, but don't forget the t. And thirdly, please simplify this. Please simplify this. What is 1 minus 0.098? Maybe you got to use a calculator for that. It should be, so 100 minus 9.8, I kind of got to do this, is 90.2. So this is going to be 0.902. I'm trying to avoid calculator use of that. 0.902 all raised to dat t power. All right, so that's the model. So the Toyota Tacoma Sport averages over time, and I think I researched this. I think this is accurate. It's not perfect, but I think that there was a value in 2021 and things like that. And I think I figured out this was kind of the average depreciation of it from its original MSRP. Anyway, you don't need to know that. So now we're going to figure out here what is the value in 2021, what was in this case here, without looking it up. So we do 38180 times 0.902. Was it the 2020 first power? No, 2021 is how many years after 2016? I know you know the answer, but you subtract. It's 5 years. 5 years later. So we are going to subtract, or we are going to substitute 5 in for t, excuse me, in this model. And this is what I'm going to do. I'm going to type this in the calculator. So this is the last problem. Wrapping it up, we got 38180 times 0.902 raised to the 5th power. Again, it's taking about 90% of the previous number over and over 5 times, and you end up getting a $22,000, about a $22,800 vehicle. So this is approximately, let me write this first, 227. You know what? I wrote approximately for these. That's not approximate. That's an exact number. So I shouldn't be writing approximately for that, only if I do approximate it. So let me go back here. So y does not approximately equal this. Y does equal this, but that's not our answer because we need dollars, and of course with dollars we need cents. This also was not approximated. This was exact, but we approximate it as we round. So this answer is also in dollars and cents. So this is $22,796.52. And to ask, do cents matter? Well, they do for 2 reasons. Number one, if you were recursively going from one year to the next, you can't just truncate the 52 and say, all right, do this times 0.902 and just take that off. each time precision matters. In fact, you wouldn't even use this number. You would actually use this number. Precision matters if you're going from, if I wanted to figure out in 2022, I'll do that right now. And you can do this one of two ways. You can either raise your number to the 6th power, because that's 6 years after 2016, or you can take the exact, and you got to take the exact. You can take the exact number and multiply by 0.902 and get the number. So you can't take it off. Secondly, and I'm sure a dealer won't care, and I don't know if they include cents into things when it comes to this. This is just for exact purposes. But if you only gave them 50 cents, or if you didn't give them any of the 52 cents at all, they're sorry, they won't give you the keys. Jingle, jingle. As insignificant as 52 cents maybe is for them, it also should be for you, right? So you might as well cough it up. You would probably make payments on it anyway. So, okay, let me very, very briefly show you how much it would be this year. And I don't know if it's accurate to this year as well. And the new cars haven't come out yet for the thing, so maybe it's still around the $22,000 thing. But I'll take the previous answer and multiply by 0.902, and I'll also show you that that's the equivalent. Oh, what did I do here? That should be a decimal. 0.902 right here. And that's going to give you about 20,500, whatever. I could have also taken the previous amount raised to the 6th power, and we should get the exact same answer as that $20,000 answer. So that's what's happening there. As one more time, I'll look it up for myself, and I'll tell you in the description section down below whether that's accurate to something now or whether you have to wait about another 6 months till it becomes that value. All right, guys, so that ought to do it for this one here. This is Mr. Robinson. Thank you so much for watching. I hope that this helped you, and I will see you in the next one, where we are going to eventually be dealing with imaginary numbers. I'm not joking. I'll see you in the next one. Take care.